everyone, welcome to the course of Digital Signal Processing. Today we will continue chapter number 4, lecture number 9, sampling of continuous time signals. And today is our last lecture of this chapter. Previously we talked about discrete time signal processing of continuous time signals. In today's lecture we will discuss continuous time signal processing of discrete signals. Along with this we will also discuss upsampling and downsampling. Upsampling is mostly called interpolation and downsampling is mostly called decimation. So let's get started with today's lecture. So in continuous time signal processing of discrete time signal, we have discrete signal at the input followed by discrete to continuous time converter, followed by continuous system, followed by continuous to discrete time converter, and finally we have discrete output. So we know that from the definition of ideal discrete to continuous converter that the spectrum xc j omega and therefore yc j omega will necessarily be 0 above the sampling frequency, that is omega greater than pi by t. So you can see in equation 4.57 and 4.58, these equations must be familiar to you. This is the equation of D to C converter. So we are reconstructing the signal xc of t from the samples of x of n, and similarly in 4.58 we are reconstructing the signal yc of t from the samples of y of n. So what we do, we multiply x of n or y of n with the shifted impulses, with the shifted sinc function. So sine pi t minus nt divided by t divided by pi into t minus nt divided by t. This is the sinc function. So at every sample of x of n or y of n, a complete sinc sits on the top of each sample, and then we multiply and then we add it by giving a shift of sampling time. So that's how we can reconstruct the xc of t and yc of t. So let's move on to next slide and see how the mathematics of the continuous time signal processing of discrete time signal looks and how the block diagram looks like. So as I told you in previous slide that we have a discrete signal at the input, we have discrete signal at the output, and this whole system is basically what? This whole system is a discrete system because it has a discrete input and it has a discrete output. Previously we have continuous input and continuous output, so we were calling the whole system as a continuous time system. Anyways, this whole system is discrete, so we are representing with the impulse response h of n and with the frequency response h e raised power j omega. So we have a discrete signal, so we will convert discrete to continuous, and we will use continuous time system with impulse response hc of t and frequency response hc j omega. The output of the system will be continuous, and then we will sample it. Why we need to sample it? Because we want a continuous time, discrete time output. So we know the relationship between x of n and xc of t, y of n and yc of t. So this is the relationship that we can obtain x of n by sampling xc of nt, and we can obtain y of n by sampling this yc of nt. So if you look at the block diagram, let me rub this. So if you look at the block diagram, the first equation that comes into mind is that we have a discrete input, and then we have D to C converter, and then we get xc of t. So obviously the spectrum of xc of t will be xc j omega. And what does discrete to continuous converter does? It is basically a reconstruction filter which provides a gain of t, and select only one copy of what? Only one copy of this x of n. So the Fourier transform of this x of n is x e raised power j omega. Because we are converting into continuous time, so we are representing x e raised power j omega t. So this is the Fourier transform of x of n, and this is the filter gain, and obviously filter cutoff will be less than pi by t. So once we have xc j omega here, the Fourier transform of xc of t, what we are going to do? We're going to pass this signal through this system xc j omega. So the output will be yc j omega. So this is the output in frequency domain is equal to, this is the frequency response of the continuous type signal multiplied by the spectrum of xc of t. Okay, again same limits. Now finally what we have to do into C to D, we know in C to D whenever we do sampling we get a gain of 1 by t. So 1 by t is because of C to D. And which signal we are sampling? Actually we are sampling this yc of t. So what will be the spectrum of this? After sampling this will be yc j omega. Because we are considering discrete, so we will replace this yc j omega, and we are not considering the copies because of the limit. We're just going to talk about the copy that is at 0. So now let me rub this whole thing out. So now I have the equation how I can find. We know that yc j omega is this thing, just substitute it here, and we know xc j omega is this thing. So if you put xc j omega here and yc j omega here, we get the output y e raised power j omega, which is written below. So once substitute all these values in equation 4.59, we know that the overall system frequency response is what? Basically the overall system frequency response is equal to hc j omega. Only thing is that you need to convert continuous angular frequency to discrete. So this is the equivalent frequency response of the system that we saw in figure 4.16. So the continuous time frequency response is equal to discrete time frequency response, since the spectrum of continuous time signal is 0 for omega greater than pi by t. So xc j omega may be chosen arbitrarily above pi by t. So most of the time our frequency response is also 0 above omega greater than pi by t. So here in 4.6 section we will talk about changing the sampling time or sampling rate using discrete time processing. In many cases it is required to change the sampling time of a discrete time signal to obtain a new discrete time signal representation of continuous time signal. So previously we were using this relationship x of n is equal to xc of nt. So the sampling time t is fixed. So what we can do, we can obtain another discrete time signal. This is another discrete time signal obtained from the same continuous time signal, but we are representing it with dash because now we are using some different sampling time. So as you can see that we have changed the sampling time. Now t dash is not equal to t. One approach to obtain the sequences x dash of n from x of n is to reconstruct xc of t from x of n. So sometimes we are required to change the sampling time. So there are two ways by which we can change the sampling time. Let's move on to next slide and see how we can change the sampling time. So the first method of changing the sampling rate is reduction of sampling rate by integer factor. So whenever there is a reduction in the sampling rate, it means we are doing decimation. So this D represents decimation. So reduction also means compression, decimation, and one thing you must be clear that whenever we compress a signal, it means that now we have fewer samples. So we have a continuous time signal and we are reducing the sampling time. We are compressing the signal, so it means that the samples are getting lost and we are having few samples in discrete time signals. So whenever we do something like that in time domain, our spectrum in frequency domain expands. So you are compressing a signal in time domain, ultimately the spectrum will expand in frequency domain. So how we can do decimation? So rather than using x nt, we have introduced an integer that is m. We have introduced an integer that is m. So what we are doing, we have a discrete time signal, we are passing it through the compressor, and then we are sampling it. So xd of n is equal to x nm, that is sampled, and then sampling period will be, here the sampling period is t, here the sampling period is mt. Okay, so now we will look into the spectrum, and before looking at the spectrum, how the spectrum expands, let's have a look at the equations of the sampling first, in which we are using mt rather than using simply t. So now you can see here the sampling period is not simply t, it is rather mt. So here m is basically the value of the compressor, the factor by which you want to compress the time domain signal, and it is also known as downsampling. And most of the time in many application we use downsampling as a pre-filtering. So you know that the Fourier transform of x of n, whenever I have a signal that is continuous time signal, I will sample it like xc of nt, and the Fourier transform of x of n will be this. The Fourier transform of x of n will be x e raised per j omega, and then after sampling we get 1 by t, and these are the copies of the original signal. Okay, so now what we have to do, we have to change this Fourier transform. We have to change the Fourier transform because now we want to decimate the signal in time domain. So x d of n is equal to x nm, where x nm is equal to x nt. So it means that now t dash is equal to mt. So wherever you have t, you can replace this t with t dash. Okay, so wherever you have t, you can replace this with t dash, and finally you can put the values of t dash, that is mt. So here, from here you can see that we are dividing something. So one thing to know is that 1 by mt will be the amplitude of the spectrum. So the spectrum amplitude will go down, so you will see the height of the spectrum will go down. Likewise, whenever we divide axis with something, the axis will expand, so you will see that our spectrum is expanding. So let's move on to our first example of downsampling. Okay, in downsampling, spectrum will expand, keep in mind. So this is our continuous time signal spectrum with maximum amplitude of 1. Omega ns is Nyquist frequency, that is the maximum frequency. This signal is band limited. Now this is the sampled version that we get after convolving this signal with periodic impulse train, and the height of this will become, or the scaling of this become 1 by t. So we have a copy at 0. This is omega s, this is minus omega s, and the heights of all these are 1 by t, 1 by t. So we have done something here. Next, what we have to do? Next we have to do that we want to change this continuous to discrete. Okay, so we have made, how we can convert this to discrete? We simply have to multiply this omega with t. So if you multiply with t, we get 2 pi here, we get minus 2 pi here, and we know that if this is 0, this is 2, and this is omega s, this will be omega s by 2. So this will become pi, because omega s by 2 is equal to 2 pi by t divided by 2, which is equal to pi. Okay, sorry, pi by t, and when you multiply it with t, it becomes simply pi. So everything is same, only the x's are changed here. So next thing is that we have to decimate it. Up till here, what we have done so far, this is the spectrum, this is the sample in continuous frequency, this is in discrete frequency, so that's why we're saying x e raised power j omega. Here we are decimating it. So what will happen? The height of this will become 1 by mt. The height will become 1 by mt, and you see these are stretched up. These are stretched up. So this point omega nt, we know that omega is equal to 2 pi by t into t. This become 2 pi, and we know that our decimation factor is 2. So what we will do, just divide it will be 2. So this point will come to pi, this point will come to pi. Likewise this point will come to pi, because we know that we are decreasing the sampling time. We are decreasing the sampling time with 2. So obviously when we are decreasing the sampling time with 2, these 2 points will join up, because we know that if our sampling frequency is 2 times the maximum frequency, we will have that much gap. Okay, otherwise these 2 points will join, and you can easily find out what point is this. So as I've told you, this is pi and this is also joined, so our spectrum is stretched up, as you can see here. Now we have replaced 1 by mt with t dash, and then we have transformed our, you can see that we have omega is equal to capital Omega t dash here. Now we are replacing again to continuous frequencies. So we have replaced xt e raised power j omega nt, and now our frequencies are in capital Omega. So how we can obtain in capital Omega? Just divide it by t dash. So after dividing with t dash, so this point will become 2 pi by t dash, this point will become minus 2 pi by d dash, and these are next copies. So these are next copies. So what happens is that our spectrum expands. Okay, our spectrum expands. So this is the frequency domain illustration of downsampling. Let's move on to next slide. In this slide we will talk about downsampling without using pre-filtering and with using pre-filtering. If we do not use pre-filtering, the copies will mix up, as you can see here in figure C, and you can see in figure F that we have done the same downsampling, but the copies are not getting mixed up. So first of all, this is our spectrum. This is the discrete time Fourier transform of the sampled version. So we have 1 by t, and this point is omega n, because this is omega n, and you know that we have converted into discrete. So omega n into t will be omega n. So this is omega n, and this is pi by 2, because this point is pi, this point is pi by 2 pi, so this will be obviously pi by 2. The spacings are equal. Okay, so now what we have done, we are compressing it with a factor of 3. So once we compress it with a factor of 3, our spectrum will expand. So now this point, the point which was initially at pi by 2, we have to expand it. So for expanding it, we have to multiply. Obviously we have to stretch it. So in order to stretch it, we have to multiply it with 3. So once you multiply, because previously we have omega is equal to capital Omega t, no downsampling at all, but now we have omega is equal to m capital Omega into mt, and the value of m is 3. So it means that wherever we have t, we will multiply it with 3. So now this point will come to 3 pi by 2, and likewise you can find out this point. This will obviously go beyond 3 pi by beyond pi. Okay, it is not difficult to find this point, because we know that this point is what? This is omega s minus omega n point. Okay, and omega s here is 2 pi by t minus omega n. So you can find out this point. Anyways, the important thing to learn here is that because we have lowered the sampling frequency. Why we have lowered this sampling frequency? Because we are using m is equal to 3. So it means that our sampling frequency is not twice. It's almost less than the twice. Okay. So once it is less than the twice, the copies will mix up. So you can see here our copies are mixing up. This point pi by 2 will go to 3 pi by 2 because in frequency it will stretch up. Okay, it will stretch up because according to the equation, whenever we have something like this, our signal will expand in spectrum. So what we are doing, we are using a decimation filter. So the value of decimation filter will repeat itself. So it is in discrete domain. So we have copy at 0, at 2 pi, at minus 2 pi, and the limits of decimation filter will be pi divided by m. So here m is 3. So what we are going to do, we are going to pass this signal x e raised power j omega through this. So obviously pi by 2 is greater than pi by 3, so it will go outside. So the filter will cut it up and we will have this thing with minus pi by 3 to pi by 3, and then we have pi, 2 pi, minus 2 pi. So now we have what we did, we pass x e raised power j omega through this filter. Now we have performed the pre-filtering in order to avoid aliasing. So now this pi by 3, if you multiply pi by 3 with 3, so now this point will go to pi. Okay, so you can see here that the copies are not mixing up. So here we have performed the downsampling. You can see here that now this t is replaced with t dash. So we are multiplying the x's, so they are expanding. Now let's have a look at the other way around thing, that is upsampling. So before we move to upsampling, this is the overall block diagram of downsampling, general system for sampling rate reduction by m. So we have a discrete time signal or its Fourier transform. We pass this discrete time signal through a filter, that is low pass filter with a gain of m and a cutoff frequency of pi by m. We get the same discrete time signal and then we finally downsample it. So we get decimated signal as we have seen in the previous slide. So here we want to increase the sampling rate by integer factor. One thing to note that we are using the integer factor. In previous two examples we used 2 and 3 to downsample. Here we use integer number to increase the sampling rate. So this is the definition of interpolation or upsampling. So what we are doing, interpolated discrete time signal is basically what is equal to xc and t, where t dash is what? T dash is equal to t by L. So we are increasing the samples in time. We are increasing the samples in time because we are expanding the signal in time. So once we expand the signal in time, it will compress in frequency domain. Okay. So x interpolated is equal to xn by L, where this is equal to xc and t divided by L. So this is interpolated signal. Now we have expanded this signal and now we are performing the sampling. So first we have to interpolate, then we will do sampling. Okay. So the system on the left is called a sampling rate expander. We will look into the next slide, figure 4.24, how the expander block diagram looks like. So here xe represents the expander and we know that expander is equal to xn by L. Let's move on to next slide. So this is the spectrum of band limited signal. This is the discrete Fourier transform. So the signal is converted from continuous to discrete, and we have missed many steps here, and finally we get omega axis. Now you can see that these points are touching. It means that this is the sampling frequency that we have used is equal to 2 times the maximum frequency. Next, what we have to do, we want to expand. So expanding means that we have to shrink this. So this pi, because we are expanding with a factor of L, so this pi will now become at pi by L. This 2 pi will come to be 2 pi by L. So it's simple. Now our axis as omega is equal to pi t. Just remember this thing, that whenever you are expanding, the spectrum will compress with a factor of L. So for compressing you have to divide, for expanding you have to multiply. So here is the expanded spectrum. Okay, so now we are having more copies. Previously we have copy at 0 and we have copy at 2 pi. Now we have 3 copies at 0, the other one copy is 2 pi by L, and then we have a copy at 4 pi by L, which is equal to 2 pi. So now we are having more copies. Okay, now this is an interpolated filter. So as we have used the decimated filter, we are using an interpolated filter here. So once we did the expansion, we are using the interpolated filter here. The gain of the filter is L and the cutoff limits are minus pi by L to pi by L, and then these filters are repeating itself. So we pass this expanded signal through this filter. So what happens, we will get this first copy, and then this copy will be skipped. This copy of 2 pi by L will be skipped, and then this signal will be passed. So what happened here is that, and obviously the gain will be changed to L by T, because the gain of the filter is L and the amplitude of this is 1 by T. So 1 by T into L will be L by T. So now you can see here the copies are moved. Previously they were close. Okay, so interpolation. Whenever we do interpolation, the spectrum compress and copies go away. In decimation, the spectrum gets expand. The spectrum gets expand and copies come close together. So let's move on to next slide. So one thing to remember is that we can also use non-integer rational fraction for sampling rate conversion. So as you can see here, we can use sampling time to be 3 by 2 times the original sampling time. So it means that we are compressing with a factor of 3 and we are expanding with a factor of 2. So here interpolation is with a factor of 2 and decimation with a factor of 3. So interpolation, expansion or upsampling all are same thing. Decimation, reduction, downsampling all are same thing. So let's have a look at an example in which we are performing all the functions, that is upsampling and downsampling. So these are the separate blocks of interpolation. As I've told you that in order to avoid aliasing, we use a decimation filter. So this is a decimation filter, and then we are performing the downsampling. In upsampling, we first upsample the signal, then we use a filter, as you have seen in previous diagram. So this is x of n. Upsampling, this signal gets expanded, we pass it through the filter, and we have the interpolated signal. The sampling time here is t by l, the sampling time here is t by l. Then whatever the signal interpolated signal is, we pass it through the filter. The sampling time remains same. Now finally what we do, we pass that interpolated filtered signal through decimation. So now the sampling time become t into m by l, and we know that the value of m is 3 and the value of l is 2, so it is 1.5. so it is what's changing the sampling rate by a non-integer factor. So if I combine this overall block diagram, so we have the discrete signal, we are doing upsampling, the expansion, and then we combine the filter. Because this is low pass filter, this is low pass filter, the gain of one filter is L, the gain of other pass filter is 1, so the overall gain will be L. Now we have to choose the cutoff frequency. We use the cutoff frequency that is minimum. If pi by L is minimum, which we will choose it. If pi by M is minimum, we will choose it. So now we are using just one filter. So first we will perform interpolation, then we will pass it to the filter, and then we will expand it. So let's move on to next slide and have a look at the overall sampling process with upsampling and downsampling. So here's the spectrum of the original signal. Here's its discrete time Fourier transform, the sampled version. You can see here the copies are almost not aliasing but just too close. Okay, so this is 1 by t, the amplitude. This is in discrete Fourier transform, as you can see here. Now what we are doing here, we are doing the interpolation here because we are changing the t to t by l. Okay, so we are compressing the axis, we are dividing by l. So this pi point will come to pi by l, this 2 pi will come to 2 pi by l, and so on. Okay, nothing will affect here. Now we will pass it through the filter. So because pi by 3 was minimum compared to pi by 2, so we have used the cutoff frequency to be pi by m minus pi by m, then its copies. So this is the decimation filter that we are using here. So once we are passing this xe, the expanded signal, through this, so obviously this pi by l, the value of l is 2, so this is pi by 2, this is minus pi by 2. So if we pass this through pi by 3, so the cutoff will be pi by 3, so this will cut off at pi by 3, so we will get this interpolated signal. Now finally we pass it through we have to downsample it. So whenever we downsample it, it means that we are multiplying. So you can see here m is multiplied with t. It means that this point, which is at currently pi by 3, and we are decimating with a factor of 3. So this pi by 3 point will go to pi, because pi by 3 into 3, this will go to, this point is not at pi by 3, this will go beyond pi. Okay, so this is how we can expand this signal.